So very good afternoon to one and all. So in this series of first inception, we are going to learn the various types of deformation process and their behavior on the properties of a material. So first, we are going to see the uniaxial deformation. So the deformation is nothing but the plastic region of a system. So we can define a system by its two properties like elastic and the plastic region. In plastic region, it meant that we had a permanent deformation in the material, whereas elastic material means that if you once unload the material in this region, the material will regain its properties. So in uniaxial deformation, so so we can define a deformation like a moment of slip planes is known as a deformation. So a body can be deformed using many modes like tension or the compression. That is nothing but the uniaxial deformation. Then we have like bending, shear, and the torsion. So all these are divided on the basis of their application of the force and the area application of it. So in uniaxial deformation, we see that is nothing but the tension and the compression. The load is acting in only one direction, as you see here in tension and in compression. So the uniaxial deformation means the load is applied in only one direction. So basically, we know that pulling an object, pulling an object is nothing but an tensile loading, where pushing an object nothing but a compressive loading. So here the force per load applied is uniaxial. So what is the major testing procedure for finding the uniaxial deformation? So we have various techniques to find the tensile strength or the tensile deformation of a system. So the basic used machine is nothing but the UTS or the tensile testing machine. So in this tensile testing machine, we see that we had a moving crossboard, the load cell, the extensometer basically mean that it is an strain gauge, and we had a specimen. So we can see that the specimen is made according to the ASTM standards. Here you can see that there is a reduction in area in between the two sections of the rod. So that means that there is a variation in the cross section. So you may ask the question that why the cross section is different in this region. The main reason is that these are two or nothing but the holdings, and this is the where the real tensile is going to take place. Here the you can say the stress is nothing but the force per the unit area. So here the you can see the same force is applied throughout the cross section of every cross section of the specimen. As we're reducing the area in this section, so we can increase the stress, and you can see that a deformation will be occurred in this region. And the deformation is favorable in this region because we can record by using an extensometer. The basically is nothing but strain gauge. Therefore, we can know the yielding strength of the material. So you can see that the L naught is the gauge length, which is given by L naught is equal to nothing but 5.65 under root of A naught, where A naught is nothing but initial cross section of the specimen. So now you can see that how the curve is generated by load versus the strain curve. So here you can see that S is nothing but stress and E is nothing but the strain. So the region O, E, P, Y, N, and F are all defined on this curve, where you can see that within the region O to Y we have other 2 points like elastic limit on the proportionality limit. And the region y to n, we had other region, and nothing but you can say that uniform deformation region with the n to f is nothing but non-uniform deformation region. So you can see that O is the point of starting of the load or the unloaded specimen, you can say, and O to Y is nothing but elastic region. So all these are terms of the microscopic event, and N is nothing but the ultimate stress region where the necking begins and affects the fracture point. So when we increase the stress in this, nothing but the load in the specimen, you see that the gradual increase in the strain or the stress in the material is nothing due to the property of the material to oppose it. So you can see that within the elastic region, the curve is linear, and the curve deviates from its linearity beyond the point known as the propulsional limit. So after that, we had a point known as the elastic limit, where you can see that beyond this point, if you load furthermore, so it will convert into the plastic region where the permanent deformation is taking place. Then we have something like a yield point where the permanent deformation can be seen in the material. If at this point, if you want to know what is the deformation occurred in the material, we unload at this point vive. So if we unload the specimen in this at vive, it will trace the curve path this like this. So you can see that there is some restraint thing and some nothing but you can say that it is restored. So the restraint is nothing but the plastic region, and the restored one is nothing but the plastic elastic one. So y is nothing but the yield point. Upon the increasing the load due to the further ordination of the forces, the force increases. You can see that the dislocations are going onto the top of the surface. So at this position, you can see the dislocations reach the surface of the material or the grain boundaries. So you can see that beyond this point, the stress is increased because to cause this dislocation to move further, which are at the surface, we need some additional force. This additional force is causing the dislocation to move further and form a free surface. So there's an increase in the stress value. So at necking, you see that the deformation, atomic debonding is starting to take place. So from this region to N to F, we can start to think like localized deformation takes place, and the material is going to fail at the point fracture F. So we have seen nothing but engineering curve versus. Now let us see the what is the true strain. So we in the engineering thing we always see with the original or the initial values of area and length, whereas come to the practical testing where the area of cross section is constantly changing. So in terms of true stress and strains, we go with the instantaneous area and instantaneous length, so which are more practical to use in the case. So you can see that stress is defined as a P to that of A I is nothing but instantaneous area, and the true strain is given by change in length to that of original length, summation of L naught to L, because the L is changing with respect to the time. And you can see there is a engineering strain which is given as a force to that original area, and the strain is given as change in length to the original length. So here you can see that the necking phenomena you can't observe in the true stress strain curve. This is the reason because here you can see that to cause the continuous flow of the material as the area we're taking as instantaneous, so area at this point is very less compared to that area beyond this point. So to cause the continuous motion of the material, so the force is increased, nothing but the stress is increased. So it is observed in this curve. So now we have seen what is actually happening in terms of microscopic point of view. Now let us understand how microscopically the deformation is taking place. We know that the deformation majorly causes to that of moment of slip planes other by twinning. So we can see that the majority case we see that moment of slip is very predominant than the twinning. So now we are going mainly based upon the moment of slips, which in turn the dislocations. So we know that as a force is uniaxial, even though we have the axial force, this axial force will not the same effect on this plane because the slip planes and the directions in turn slip planes are the closed path planes where the dislocation propagates. So these slip planes and directions are oriented with certain angle with the uniaxial force. So as you're appearing, so the variation of the force in magnitude changes with respect to the slip direction and the plane. So even though we have done the same apply for throughout the cross section of it, at each plane and direction, it is very different. So now understand. So P is nothing but you can see that it is nothing but the elastic. So yield point in the previous graph. Now let us understand how it is taking place in a microscopic point of view. Now we can subdivide into it like 0, O, A, B, C, D, and P. So 0 to A is nothing but truly elastic in nature, region where the dislocation do not move at all. And the region A to B is nothing but it's also elastic, but the dislocation starts to move but do not leave the greens. So on reversal of the load, they return to the original configuration. So beyond this point, you can see that it is nothing, not no more microscopically elastic. So it is converted into the plastic regions where the dislocations are moving out of the grains. So the region B2D is nothing but the microscopic plastic region, but we can't see this by the in terms of microscopic point of view, where entire region is considered to be as elastic in terms of microscopic point of view. So in terms of microscopic point of view, we consider Z to be as an elastic and B to D as plastic. So now you've seen what is happening beyond the point yield. So you can see that here the strain hardening and the piling of dislocation is taking place. As the dislocations move to the free surface of the material, now due to the so many dislocations at the surface, they need certain energy or the certain force to come out of the surface. This energy is provided, and you see that increase in the strength of the material in this region. So this moment of dislocation is seen as a step due to the piling of it. So you can see that region Y2S is nothing but the uniform deformation is taking place. So beyond this is we see the necking starting to take place. The atomic debonding has taken place, and due to this, the voids are created. Due to these voids, localized deformation takes place, and the material is going to deform non-uniformly till B and get fractured at the point B. So if we consider the deformation comparison between the brittle material and the ductile material, so ductile material is the one where the plastic deformation is very more, whereas in brittle material the deformation is very less. So if we want to find from an tensile stress the difference between the ductile and the brittle material, you can see the cup and cone shape is formed on a brittle material on a ductile material and a flat plane of an brittle material. So when we go to the fractals of this material, you can see that the dimple formation is very dense in the brittle material where they do not propagate too much and they break in between before propagation of it. Whereas in the ductile material, the dimple density is very less and the dimple size is very big. Eventually you can see as an fractal structure. So this dimple formation is sign of an ductile nature, whereas an flat plane structure is a fractal or signature for the brittle material on the tensile loading. Thank you. So this is the first lecture under the series of the first inception of understanding the deformation of a material. In the next following lectures, we are going to understand what are the various deformation phenomena, the grain size, and how it is going to affect the system in terms of the properties of a material. Thank you.